Hi everyone. So remember that last time we had introduced this notion of a linear transformation as a transformation that satisfies these two conditions. One condition has to do with addition, that t of x plus y is equal to t of x plus t of y, and the other condition has to do with scalar multiplication, that t of k times x is equal to k times t of x, when k is a scalar. So now we're going to try to get some geometric intuition for these conditions. So we'll draw pictures where t is going from R2 to R2 because that's the case where you can actually draw the pictures nicely. But in a lot of ways, the two-dimensional case will give intuition that can apply to higher dimensions as well. So let's say we have some vector x in the domain. We can plug that vector x into t and get some vector in the image, which as far as we know could be anything. And then similarly, I could pick some other vector y in the domain and plug it into t and get some image vector. I'll just emphasize that the logic behind this is that I just picked the vectors on the left at random, plugged them into t, and got some vectors on the right, which the vectors on the right should be determined by t, but in this scenario, we don't have any information about t at all. So the vectors on the right could be anything. And so I just drew random pictures just so we have a picture. Now recall that addition of vectors has this nice geometric interpretation by the parallelogram rule. So we can represent x plus y as the vector that goes to this other vertex of the parallelogram spanned by x and y. And now, when we look at the linearity conditions, we see that when we plug in x plus y into t, we get t of x plus t of y. And so as a result, t of x plus y also satisfies this parallelogram relationship with t of x and t of y. This is because of linearity that this happens. If you had a nonlinear transformation, then you wouldn't necessarily expect to be able to know anything about t of x plus y just from knowing t of x and t of y. This comes from linearity. And so the moral here is that linear transformations preserve parallelograms. And what I mean by that is that if you have a parallelogram in the domain, and you take those four vertices and you plug them into t, then you'll get vertices that form a parallelogram. It won't necessarily be the same parallelogram. The shape could change, the angles could change, the lengths could change, but parallelograms will turn into parallelograms. Okay, so now again, let's suppose we have a linear transformation, and let's suppose we have a line in the domain. One way to describe this line in terms of vectors is to first pick a point on the line, and let's call the vector that goes from the origin to that point v. And then let's pick any vector that's parallel to the line and call that w. So then when we add v plus w, we'll get another point on the line. And in fact, we can do better. We can get all the different points on the line by rescaling w. And so we can get all the points on the line by looking at everything of the form v plus t times w for different values of t. So for example, v plus 2w would be over here, v minus w is over here, and so on. So then what happens when we plug all the different points of the line into the linear transformation t? Well, we can use the properties of linearity to split this into two terms and pull out the scalar. And we can see that the result, again, looks like the description of a line, because it's a vector plus t times some other vector. Okay, so without more information, we don't know exactly what t of v and t of w are, so I'm just drawing some vectors at random for the picture. But once we have those two vectors, then we get all the points on the line in exactly the same way as we did in the domain. So you'll notice it's not the same line as before, but it's another line. So the conclusion is that linear transformations preserve lines, in the sense that if you have a line in the domain, when you plug all of those points of the line into t, you'll get another line in the image. So this is kind of cool. It's nice to see these interesting properties that linear transformations have. But how does this actually help us do stuff? Well, it's actually possible to define some linear transformations using geometry, and then use geometry to prove that they're linear. And then because we know that every linear transformation corresponds to a matrix, we'll know that there's some matrix out there and we can figure out what it is. So I'll give you what I think is the most important example in the sense of being both useful and illustrative. And that's the example of rotations. So let's say that T is a transformation from R2 to R2, which rotates vectors counterclockwise by angle theta. So that means that it keeps the length the same, but it just rotates them. So let's say if I pick some random vector v in the domain, you get T of v just by rotating v by theta. So I claim that this transformation is linear, and I actually don't need to do any calculations to prove it. I can prove it purely using geometry. All right, so let's say I have two vectors v and w. We know that the sum of the two vectors is given by the parallelogram rule. And then we can think about what happens when you plug these vectors into T. Well, T rotates them counterclockwise by theta, and so all of these vectors will be rotated by theta, by the same theta. And then the important thing to observe is that if you take a parallelogram and you rotate it, it's still a parallelogram. So T of v, T of w, and T of v plus w still form a parallelogram, and because of that we can conclude that T of v plus w is equal to T of v plus T of w. And I won't draw the picture, but you can make a similar argument for scalar multiples, that if you multiply a vector by a scalar, that changes the length of that vector. And if you think geometrically, it's pretty clear that if you rescale and then rotate, you'll get the same thing as if you rotate first and then rescale. And so then that tells us that T of kv is equal to k times T of v. And just remember, these two equations are the equations that tell us that T is linear. So then, now that we know that T is linear, we can try to find the matrix that it corresponds to. And remember, the way that you do that is that you look at these two standard vectors, E1 and E2, and then you plug those into T and see what you get. And in this case, at least in terms of the picture, we know what we get because the vectors just get rotated by theta. But the question is, what are the actual coordinates of these vectors? And for that, we use trigonometry. We know that the length of the vector is 1 because E1 has length 1 and it's just been rotated. So then you can form a right triangle where the base is cosine theta and the height is sine theta. And so from that, we get that T of E1 is cosine theta, sine theta. And then you can do a similar thing for E2, but note that in this picture, E2 is pointing in the negative x direction, so the x-coordinate is actually minus sine of theta. So T of E2 is minus sine theta, cosine theta. And now we have enough information to write down A, because the columns of A are these vectors that we just found, T of E1 and T of E2. So you get this formula for A, and this type of matrix is called a rotation matrix, because when you multiply it times a vector, it rotates that vector. You see rotation matrices coming up in a lot of physics and engineering applications, so you might have seen them before, actually. But also I'll point out that this matrix is used in your phone when you rotate a picture. You could also look at rotations in 3 dimensions. These transformations are also linear, but it's harder to write down a general formula like we just did in 2 dimensions, because in 3 dimensions there are lots of different ways that you can rotate something. You can pick any line through the origin and use that as an axis, and then you can rotate about that axis. And so there's lots of different directions you can rotate, and it's a more complicated situation. But there's a lot of interesting algebra in these rotations, and they're useful for a lot of things such as computer graphics. All right, so another important example is orthogonal projections. So the setup here is that you have a line through the origin, and then you can define a transformation as follows. Given a vector v, you drop an orthogonal onto the line, and then whatever point you hit on the line determines a new vector, which is T of v. So T of v is always parallel to the line. And so, just like with rotations, I can use geometric arguments to explain why this is linear. Suppose I have another vector w, and I want to add w to v. Remember that one way I can think about addition is sticking the vectors head to tail. And then v plus w is the vector that goes all the way to the end of w. And then when you drop a perpendicular from there, you can see T of w, and you can see that T of v plus w is exactly what you get when you put T of w head to tail with T of v. So we can conclude that T of v plus w is T of v plus T of w, and you can make a similar argument for scalar multiplication. I'll leave that as an exercise for you. So since t is linear, there should be some matrix such that multiplying by that matrix has the same effect as plugging a vector into t. In order to get a formula for that matrix, you need to pick a vector u that points in the direction of the line. If we write u equals u1, u2, then the matrix that corresponds to this transformation looks like this. You'll notice that the formula is kind of complicated, and I'm not even going to try to explain where it comes from. It is possible to do it using the method of the previous example, but later on we're going to have some better tools that will make it easier and more intuitive. The reason I wanted to show this to you right now is that this is a good example where the geometric description of the transformation is much simpler than the matrix. And there are questions you can answer using the geometric description that would be quite difficult to answer using the matrix itself. Here's a good example. Which vectors satisfy the property that a times x is equal to x? This is something that you could express as a system of equations and solve. And it would take a decent amount of work to do, but you could do it. But then on the other hand, if you just think about this transformation geometrically, you can almost see what the answer is right away. It's the vectors that are on that line, that yellow line. Because if you have a vector on that line, when you project that vector onto the line, it doesn't change the vector. It's just the same vector. And on the other hand, if you have a vector that's not on that line and project onto the line, then you're going to get a different vector. So it's exactly the vectors that are on that line that satisfy the property that a times x is equal to x. And in fact, we can write that solution in a form that looks like what you get when you do Gauss-Jordan elimination, where there's a free variable, and the solution in this case would be x equals t times u. And that came completely from the geometry. I'm not messing around with this matrix right now.